This is geometry, the first day of Unit 3. We're going to talk about some vocabulary. We're going to start with conditional statements. A conditional statement is a logical statement that has two parts. A hypothesis and a conclusion. We're going to write many of our statements in if-then form. We'll have theorems for proofs, and they'll always be written that way. So an if-then statement is a conditional statement in which the if part contains the hypothesis and the second part, called the then part, contains, what do you think? The conclusion. Okay, what is the hypothesis? The hypothesis is typically, it'll always be the if portion of it, but a hypothesis is a statement that we accept to be true. So, in the very beginning, we say if an angle is a right angle, we're not going to call that part false. A conclusion is a statement that we evaluate how it relates to the hypothesis. So we need to determine if the conclusion matches that of the hypothesis. So if an angle is a right angle, then it is 90 degrees. The 90 degrees matches that of the right angle. Therefore, it's a true statement. Next, we're going to talk about perpendicular lines. When we discuss perpendicular lines, we're looking for a definition. Two lines that do not intersect. Oh, I'm sorry. That is parallel lines. Perpendicular lines are two lines that intersect to form right angles. That's perpendicular lines. Two lines that form right angles. Now we're going to write that in an if-then form. So if two lines are perpendicular, then they intersect to form right angles. So we took a conditional statement and we wrote it in an if-then format. And we can see that by definition, if two lines are going to form right angles, then they are perpendicular. Parallel. I already started to do this one. two lines that do not intersect. Our if-then statement of that is if two lines are parallel, then they do not intersect. Now, for two lines to not intersect and be parallel, to be parallel, they would need to be in the same plane. A lot of times in our definition, we won't throw in the extra language for that. Of course, you could have two lines that don't intersect that are called skew. They are in different planes. But in terms of our drawings that we might do on a piece of paper, two lines are parallel if they do not intersect. Remember that lines go on forever. They're just not segments. They're full lines. A segment. A segment is a point. A segment bisector is a point, a segment, ray, or line that divides the segment into two congruent parts. The congruent parts is important here. We're going to talk a lot about things being the same measure, the same size, and we won't use the word equal. We'll use the word congruent each time. If it, and it is referring to a point, a segment, a ray, or a line, if it is a bisector, then it divides the segment into two congruent parts. So now we're going to go back and we're going to look at what the hypothesis should be for each of these. So the hypothesis here is a bisector. The conclusion, what is this bisector doing? It will divide a segment into two congruent parts. Later in our lesson, we'll talk about switching those two with a converse, but not quite yet. Up with parallel lines, we're going to talk about the parallel aspect of it, and that they do not intersect. So we have our hypothesis and we have our conclusion. I'm not too concerned if you include the two lines portion, but when we start to switch these, sometimes you leave part of the if in there. If two lines do not intersect, then they are parallel. That'll be a converse later on. So it's important for us to identify what parts are the hypothesis and what parts the conclusion. Hypothesis is always in the front and conclusion is always in the back. If the two lines are perpendicular, then they intersect to form right angles. So I'm going to circle intersect to form right angles. When we look at if-then statements, we can often decide if it's a true statement or a false statement. We're looking at how the conclusion relates to the hypothesis. If it's false, we talk about a counterexample, which is a specific case for which the conclusion, another word for conclusion you'll see in the book talks about a conjecture. A specific case for a conclusion for which the conclusion is false. So if you say an example is all students wear jeans, and you can give examples of this student wears jeans, and that student, that student, that student. A counterexample would be finding one student that does not wear jeans, might be wearing shorts. That would be enough to show that all students do not wear jeans. On our second page, we're going to be looking at some if-then statements and determining if they're true or false. In this first one, if the sum of two numbers is positive, that's your hypothesis. The sum of two numbers is positive. Then the two numbers being added are both positive. Well, if you think about the numbers 2 plus 3, that makes 5. 7 plus 5, that makes 12. These are the sum of two numbers is positive. The sum of two numbers is positive. Then the two numbers being added are also positive. It looks true, but it's actually false. And we would say false because you could still get a positive number, 7, by adding together numbers that aren't both positive, both being positive. So this is our counter example. Our counterexample would be the -5 and 12 that add to be 7. That adds to be what the hypothesis requires, two numbers that have a sum that's positive. But together they're not both positive numbers. If an angle measures 112, then its angle is obtuse. So when you think about that, what's their need for obtuse? You got to be greater than 90 but less than 180. So if you're 112, will you always be obtuse? And the answer is clearly true. Okay? If a number is a power of 2, then it is a multiple of 4. Well, there's a couple different ways you could interpret this question. We'll look at it as saying 2, the power of 2. So my power is 2. If I take another number and raise it to a power, and I take another number and raise it to a power, will it always be a multiple of 4? Well, 4 is a multiple of 4, 16 is a multiple of 4, but this 9 is not always a multiple of 4. So we get false. This is our counter example. This is an example that states that this statement is incorrect. In this case, we have 3x plus 10 equals 16, then x equals 2. So we're going to check here and take our 3x plus 10 equals 16. And when we divide, we get 2. So if we have this equation, do we get x equals 2? And the answer is yes. So it's true. No counterexample needed if it's true. Now we're going to look at a converse. Which is a statement written by switching the hypothesis and conclusion. So we're going to take the if portion, we're going to take the then portion, and we're going to switch the two around. You still say the if first, but you take the hypothesis and switch it with the conclusion. So for part A, we're going to take our statements from above, and we're going to switch the conclusion and hypothesis and see if we have a true or false statement. And if it's false, we're going to give a counterexample. So for this first one, it says if the sum of two numbers is positive, then the two numbers being added are both positive. Now we're going to say that in the other direction. If two numbers are both positive, then their sum is positive. So what do we think about that? If two numbers are both positive, 3 and 5 make 8. That is positive. 7 and 9, two numbers that are both positive. 7 and 9 are 16. To me, you can't prove something true because of examples, but sometimes it helps us to understand what's being asked. This happens to be a true statement. Part B. Up top we said, if an angle measures 112 degrees, then it is an obtuse angle. So our converse is going to be to switch the obtuse with the 112. If an angle is obtuse, then its measure is 112. So can you think of 112 degree, can you think of an obtuse angle that is not 112? And the answer is yes, you can think of many. So we could call this one false. And our counterexample is going to be 153, or any number between 90 and 180. The specific for our counterexample, we said a specific case that shows a conflict with our hypothesis. So 153 would meet that requirement. So this is our counterexample, 153. Okay, our next one here. If a number is a multiple of 4, then it's a power of 2. So multiples of 4 would be 4, 8, 16, 4 times 1, 4 times 2, 4 times 3, 4 times 4, 4 times 5. It's a multiple of 16. I'm sorry, a multiple of 4. 16 would be one of those. Is that a power of 2? So 2 to the first equals 4. That worked. 2 to the third equals 8. Looks like it's working. 2 to the fourth equals 16. That's true, but we have other numbers that are multiples of 4. So we'd call this false. And our counterexample was the 12. Okay, this last one. If originally we said if 3x plus 10 equals 16, then x equals 2. So we're going to say if x equals 2, then 3x plus 10 equals 16. Well, the question is, can we think of another equation that could have x equal to 2? Up here, could we think of another angle that makes it obtuse? Could we think of something other than positive that you get two numbers to both be positive? If two numbers are positive, we're only going to get positive. In this case, we can think of another angle that makes this true. Here, I can think of another equation I can think of x minus 3 gives me negative 1, and x would have to be 2 in that case. So here's another equation when x equals 2. If x is negative 2, then this has to be the equation. The answer is false. I have an equation that x is still 2.